All right, CNBT 1311, we're back again. Video 2 in Chapter 11. Calculating heat loss in cold weather and heat gain in hot weather is necessary to size the heating and cooling equipment required for a building. Aren't you glad you took this course so you understood that? Let's scroll down here to the bottom of this page. For more detailed information, on the calculation of heating and cooling loads, refer to the handbook published by the American Society of Heating, Refrigerating, and Air Conditioning Engineers, known as ASHRAE. Boy, I spent hours and hours and weeks in that bloody handbook over the years. Again, the purpose of this is not to turn you in to ASHRAE engineers. Heating load. Here's the definition of heating load. 1, 2, 3, 4. Okay? All right. A BTU is a British thermal unit. Okay? The load's the hourly rate of net heat loss in an enclosed space. It's expressed in BTUs per hour. All right? That's just the base. It's a British thermal unit. It's the quantity of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. Now, I know y'all were just dying to learn that. A degree day is a unit that represents 1 degree of departure in the mean daily outdoor temperature. All right? It's used to compute the heating and cooling loads and size the HVAC system to calculate yearly fuel consumption. Yeah, we do that. You bet. Oh, yeah. But there is an efficiency rating on all the units now. All right, heating degree day is 1 degree per day, or 1 degree day below the standard temperature of 65 degrees Fahrenheit. All right, cooling load, it's the hourly rate of heat gain in an enclosed space. Heating load is the heat loss. Cooling load is the heat gain in enclosed space. All right, so it's cold out here. You want this warm in here. So heat loss is the primary sources of heat loss in cold weather. It's convection, radiation, and conduction, which makes sense, right? You go back to the original definition of those things. Infiltration of air through cracks also affect your heat loss. Heat gain, which is your cooling load, all right? And the sources of heat gain, guess what that would be? Oh, the sun coming through windows, beating on the roof, turning your attic into an oven. It's 115 degrees out here. It's going to be well over 130 at some point in that attic. Cooking, humans, activity, electronic devices, everything adds to your heat gain. So you just can't do an R value through the walls and the roof and the floor. You got to calculate the occupancy use of this space. How many people are going to be in here? What are they using? How many computers? Et cetera, et cetera, et cetera. The kitchen, the bathroom. Bathroom raises what? The relative humidity, right? And he goes through a whole list here, which I just went through. All right. Lighting, ventilation, latent heat, requiring energy to condense the moisture in warm air so that relative humidity in the space will not be excessive. You don't want to turn the inside of your building into a beach. All right. Definitions for you to read. I am sure y'all are all going to go out and go get a copy of the ASHRAE manual. I've got one buried in a box somewhere in my house. In fact, I think it's over on the bookcase. When I taught this in the fall of, the fall of 2018, and then again in the fall of 2019, 16-week face-to-face, we did go through some of these calculations. I did it. I didn't test the students on it. I made them do it in class, just so they could understand some of the simpler calculations. But again, that's not. Oh, a ton. Well, I don't want to. I would cheat you. A ton of refrigeration is the cooling effect obtained when 1 ton of ice at 32 degrees Fahrenheit melts to water at the same temperature in 24 hours. It's equivalent to 12,000 BTUs per hour. Okay, so a ton of AC is 12,000 BTUs per hour. All right. So, hint: a ton is equal to a ton of refrigeration is equal to 12,000 BTUs per hour. You don't have to worry about the ton of ice melting. You can figure out a bunch of geeks in the ancient days of yore sat around and figured out how to do this, right? Like a horsepower, right? You know, what's a horsepower? Go Google that. You'll get a kick out of that. Um, 1 horse. What size horse? Is it a Clydesdale? Is it a little roping horse? I mean, come on. But they picked a horse, and it moved so much weight in a certain period of time, and that was a horsepower. Yeah, okay. You really want to go into history, you can figure out why the railroads gauge between the rails are that distance. But I am going off into geek land again, and I apologize. Because the spacing of the railroad rails goes back to the width of a horse's ass that pulled a chariot for the Romans. Yeah. So, no extra charge of that. I probably ought to be beat with a stick for even bringing that up. But hey, forced air heating. Most of your units, most of your systems are forced air. They have to have some kind of air handling, whether it's an RTU, whether it's an absorption system. Once you get a heat or cooling source to either cool or heat or balance out the space, you've got to drive that air, and that's forced air. It's forced air heating. It's forced air cooling. All right. So in this case, you got a furnace. You got an air return. You've got to return that air. You've got to supply the air. You don't want your air supply to be so close to your air return you create a short circuit. The morons that did my house, I got a vaulted ceiling. The air return up in the upper level of the stairwell near where the T-stat is, about 4 feet over to 3 feet over, is a supply vent. I mean, it's a register that's bringing air in. So it's bringing air, heated or refrigerated, and then this big old thing is sucking it out. So we've got a little short circuit right here. And I don't have $15,000 to go in and hard duct my house right now. Solve that problem would be to hard duct it, because the architect that designed this thing didn't consider how to run all the HVAC stuff right. All right. There's gas oil furnaces. There's wood pellet furnaces. There's natural gas furnaces. You name it. Okay. So he goes through a bunch of definitions. What's a bonnet? What's a leader? What's a stack? Gathering refers to a tapered section. The boot, what's a boot? What's a manifold? What's an extended plenum? And then you've got these daisy chains, what I call a daisy chain or a perimeter heating system. You got a loop and perimeter radial system. These all have to be balanced. You got to do an air balance coming around, and to do an air balance, you bring a special company in with the airflow hoods that put over the distributors, diffusers, and you start balancing out the air. Well, they had hell doing the air balance in the welding lab at Cypress Center. Because you've got these giant exhaust fans sucking out the welding gases while you've got the rooftop units dumping in. So the welding exhaust system, the Niedermans, pulled out more air than the RTUs could put in. So the RTUs were basically dumping the supply air into a vacuum. And they were really running up on their fan curves, and they would overdrive the motors and break their mounts, and it took them a while to figure that out. They were having heck. I just said you need to put VFDs on those RTUs, that's variable frequency drives, and tie them into the SCADA system in balance, and tie the Niedermans, the exhaust system, in with the rooftop units. They ended up doing that, cost a bunch more money, and solved that problem. It is a simple engineering problem. The root cause analysis, the RCA, was not very difficult. Wall furnaces can be down wall furnaces in the wall, and the benefit of these, if you can do your architectural layout right, is you can bring in your makeup air from the outside, balance it, because remember, we still need to refresh the air in these structures, right? So he talks about that. Furnaces are in the attics, are in basements, you can put them anywhere. But they do need makeup air, because what does it take to drive a flame? It takes fuel and oxygen, right? All right. And if you looked at some of those Ringler videos from Austin, the architect, he does some unique things with the HVAC systems in those houses in Austin. Again, hot water or hydronic heating is a system for heating a building by means of water heated in a boiler, and it circulated pumps through radiators. I lived in a dorm at A&M that had radiant radiators in the room itself. Those things would get super hot, and they had extremely hot water going through them. Okay, a boiler is a closed vessel, and a boiler is controlled by the American Boiler Manufacturers Association code, building codes. Boilers have to be inspected by the state on an annual basis. This is a one-pipe system, which is a loop, and this is a two-pipe system. This down here is a two-pipe, and this is a one-pipe. As you can see from the boiler, it circulates around to all these radiant heaters around here. And this is the radiator. As we progressed in technology, they came up with a fin tube convectors that would surround baseboards. And some places of the world, these are still used. I was in a hotel up north, and I think in Scotland too they had this in the hotels in the northern part of Scotland. There's a baseboard because hot air rises and it sucks the cold air off the floor, and you had heated water that ran through here, H2O from the boiler room, and it was pumped through the system. Electric heating, all right. Comparative heat values of energy sources. Anthracite coal, you get around 14,600 BTUs per pound. Oil is 139,000 BTUs per gallon. Natural gas is okay. I'll buy that. All right. It depends on the density of the natural gas, but yeah, anywhere from 1,000 to 1,100 BTUs per cubic foot. And electricity, 1 watt 1 watt of power is 3.41 BTUs per hour. And I had some wattage and amperage calculations we'll get to later. I'm going through the 5th edition. And here's an example of the baseboard heaters. These can be electric resistance heaters. And then you can have a forced air heater here. Here's one with a fan on it that's doing forced air. This is the electric heater like I have in my shop, which is I got a thermostat and a fan, and it's on a 40 amp breaker, and I need to put a bigger breaker in it. And these kind of fans can be all kinds. They can be quartz radiated. He types a quartz heater, industrial unit heaters. They're with directional outlets, and they're designed to be suspended from a ceiling or a roof structure. These just have, the quartz heaters just have resistant heating elements, and they're sealed in quartz glass tubes that produce an infrared radiation. What you have to do is you got to balance what your BTUs and your airflow is. Again, you may need 2 of these in a space. Who knows? But each one of these needs to be on their own circuit, their own home run. So, and a home run is nothing but a line from the panel box to the appliance. All right. Here's a fully recessed floor unit, and this is a wall unit. Okay. And this is a toe space unit. All right. And they all use a fan to draw in room air and pass it over some kind of coil, whether it's a resistance heating coil, before blowing it back into the room. Electric resistance heating uses convection. Circulates by convection. Just like the baseboard hot water ones did. Cold air comes through here, heats up, and rises. Depending on how big this space is, you may need some fans. You might need to put a ceiling fan in here with a reversible switch, so that during the summer it's spinning one direction and during the winter it's spinning another. Because you don't want all your hot air to pool up here while you're down here freezing, right? Okay. But again, remember, if you're going to have to use a fan to supplement this, the velocity of that air that's circulating around in this room, the velocity of that air will cool. The faster the air moves, the cooler it is, right? So you got to balance that. All right. We talked about radiant heaters. Radiant heat travels in a direct path, and it doesn't travel around corners. All right. They can use heated ceilings or floors. We talked about running radiant heat coils in a slab when we talked about the slab video. Remember that? In Colorado, like in Crested Butte, they're up at about 10,000 feet. They get like 12 feet of snow. All those houses have some kind of radiant heat system in them. Circulates the hot water in the slabs. McGowan, a fashion photographer and the father of underwater photography, in the late 50s and early 60s in California, when he did his studio, even though it was California, he put radiant heat in his studio floor because he was doing a lot of pinup photography for calendars for people like Rigid Tools and stuff like that. So he did a lot of nude photography and pinup photography. And so to keep the models comfortable, he put radiant heat, even though he was in Southern California. We've seen this before. I think we've seen this before on the slabs of the flooring. Here's a subfloor, and they just hang the radiant heat pipes in here. And then, of course, you need thermal insulation. Um, here's an example of them buried in the concrete. Um, um, and here's an example of them running on existing joist. So these are running parallel to the joist. These are running perpendicular to the joist. There's many ways to do this. Active solar energy systems. Um, some people around this area, they have solar heating panels for water, and then they have solar panels for electricity. Um, so it's called a collector panel because it's collecting the heat from the sun, um, and it heats up water in here. It's like radiant heating in reverse, and it's circulated down through a pump. There's some kind of storage facility, um, and then there's a heat exchanger. And let's see what else we got. A heat transfer medium. It could be air, could be water, or other liquid. Air is an inefficient. Water, if it's contained, and it might not just be potable water, it could be something else, a mixture of water and another liquid to make a more efficient closed-looped system. Well, your mileage is going to vary. Um, the heat distributing components of the solar energy system are similar to those of conventional systems. Got to have some way to move the air. Got to have a heat exchanger. And all a heat exchanger is like a radiator, to put it simply. And then you blow the air through the radiator and then up into the space. And then here's your return. And here's your supply. Then there needs to be a bypass, and there's instrumentation that goes in here. And there's nothing passive about this. You need electricity to drive all of this. What does he say here? It may be in the form of a tank filled with water or other liquid medium, or a bin of rocks, or phase change salts for air systems. And it could be a salt system. Yeah. All right, heat distributing components. We talked about that. For an active solar energy system to be efficient, the building itself must be thermally efficient and well insulated. Its sitting orientation and window opening should take advantage of the seasonal solar radiation. Remember the sun angle we talked about, sun angle calculators in the site? You may get lucky and this will work for you. But if you're in a cookie cutter subdivision, you may not have a choice in the direct angle of the sun that you get. And it may be the point that it's not that efficient for you. If you've got two-story houses on both sides and you're a single-story house in between them, they may be blocking the sun. So all that stuff has to be taken into consideration. Now we get into cooling systems and heating systems, but this is mostly cooling systems, except for a heat pump, and we'll talk about that. Compressive refrigeration is commonly referred to as a DX, or direct exchange. You probably heard the term Freon. Most of ours are all air down here, not water, especially for residential. So you have a heat exchanger here, and you've got a heat exchanger over here, and you've got a compressor which compresses the refrigerant gas, and so this would be the heat's released to air or water on this side, and heat is extracted from air or water on this side. So This would be your cooling coils on the inside of your DX unit in your conventional house. The evaporator is the component of the refrigeration system in which the refrigerant absorbs heat from the cooling medium because of evaporation. It goes across an evaporation valve, an expansion valve in here, and as the gas expands, then it absorbs heat. And you'll have air, a fan that blows through this. This would be on the outside of your residence. He shows you expansion valve up here. But your expansion valve in your unit in your attic is up here with the air handler in the attic itself. And this would be on the outside where the compressor's at. This would all be housed in that big noisy thing outside with the cooling fan on it. And so this expands to a gas in here and absorbs heat, and then this condenses it back to a liquid to come back through the system. And as the pressurized liquid expands across the expansion valve, then you get the cooling effect of expanding, going from a liquid to a gas. All right. Heat pumps are a DX unit, but they work in two ways. They work. It's a two-way system, and you can read about that here. Sometimes the DX units will have to have heating coils in them to help when it gets super cold outside, because the heat exchange is not that efficient after the temperature drops to a certain point, and that depends on the unit itself. But that's how heat pumps work. Heat pumps work the same way a traditional DX unit goes, but they can run backwards. All right. One of the oldest type is an absorption refrigeration machine. These have been around for a long time, even back in the 1800s. Some of the older ones used ammonia as their cooling medium, and sometimes they would blow up, and it was made for a bad day at the ice house. But if you ever wondered how they got those giant blocks of ice to deliver on the ice wagons before we had electric refrigeration and electric refrigerators, we just had ice boxes. That's how they did it. And absorption machines are still used in industry today. They're a lot more efficient, and this describes how an absorption refrigeration system works. This concept has been around for a long time. All right, HVAC systems in and of themselves, they come in all different shapes and sizes. Let's see, heating, ventilating, and air conditioning, HVAC, that's the acronym. Simultaneously control the temperature, humidity, purity, distribution, and motion of the air in the interior spaces of the building, be it a commercial building or a residence. You have a smart T-stat or thermostat. My wife is a digital Debbie and likes all things digital. She's got 2 or 3 iPads, 2 iPhones, an iWatch, 2 computers. So naturally, when we redid our thermostat, she had to get a smart thermostat to play with the Alexa, and it's not like the old T-stat where when it's getting cold in the house, you had to go up and flip the switch to heat. This thing automatically does its thing, and of course, there are times I have to call her and ask her how to adjust the thermostat. She gets a kick out of that, especially since I'm supposed to be an engineer. Well, anyway, I digress once again. All right, now he shows a cooling tower. All right, a cooling tower is just that. This would be with a chill water system. okay, and the cooling tower with a fan up here and water cascades down here in a closed system to exchange the heat that was pulled out of the building itself. Heating and cooling energy can be distributed by air, water, or a combination of both. We have a chill water system at the Cypress Center. We have rooftop units, and RTU is referred to as a rooftop unit. These can also be DX units set on the roof and a curb. We have preheaters in these systems. You got blowers that supply, you got humidifiers, and in some cases you may have to have a dehumidifier. Here's a damper to regulate the draft in air ducts, intakes, and outlets. Exhaust air, and we're bringing fresh air in. This is makeup air. Because after a while, this air in here is going to get stale. And this is your supply, and this is your exhaust coming down to a main ductwork, and it's recycled. Unless you go to work for an HVAC engineering company as a designer or drafter, you probably won't get into this in a normal architectural environment. They'll contract this out to a mechanical firm. Chill water plant. It's powered by electricity or steam or gas, and it delivers chill water to the air handling equipment. The boiler produces hot water. So this is you'll have chilled water pipes and hot water pipes running through the building. Fan room is just that. That's the room that has all the air handling equipment. The bigger the building, the more complex the system. They contain the fans, the filters, and other components. And the filters can be electric filters. If you're running a clean room for pharmaceutical manufacturing or hospital, these filters will be a conventional filter. There'll also be UV filters to kill out the bugs in the air. Here we go back to ASHRAE again. Let's see. Over half of the indoor air quality problems result from inadequate ventilation and filtration. Building codes specify the amount of ventilation required for certain uses. This goes back to the original videos about the occupancy types, okay, and how many air changes per hour and cubic feet per minute per person. And ASHRAE recommends 15 to 20 CFM per person for most applications. Most. Do not stake your reputation on this. You get with the current building code and current recommendation based on the occupancy code of the building. This is your mechanical engineer's responsibility also. All air systems use a single duct. Okay, all right. In a single zone system, a master thermostat regulates the temperature for the entire building. In a multi-zone system, separate ducts from central air handling units serve each of a number of zones. Your commercial buildings, unless it's a single-story commercial building, are going to be multi-zone systems. Okay, so each one of these floors, let's just assume this is a high-rise. Each one of these will have their own T-stat, their own control box. He calls it a mixing box, but that's what it is. It mixes the warm and cold air to set the temperature in that room. Okay, your residences are mostly a single zone system, although there are some residences that have a split zone system, so they'll have two separate air conditioning systems for the house. So you'll see two compressors sitting outside the house, or three. Now Daikin has come up with a split zone DX system that uses a single compressor, and they use splitter boxes throughout the residence. And that system is also a multi-zone system. But unless you got lots of money, I'd stay away from Daikin. Daikin makes a very good product. They got that giant plant out off of 290 in Waller, and but Daikin will only allow Daikin to service those units, or a quote-unquote Daikin um, trained technician, and most of them have to call the engineers at Daikin to figure out how to balance the system out. Again, I'm not beating up Daikin. It's just they're a very tight-lipped company. They're a Japanese company, and they make a good unit. And when they work great. Okay. Air-water system, we've already talked about that. It uses air and water. They use high-velocity ducts to supply conditioned primary air from a central plant. The primary air draws in room air through a filter, and the mixture passes over coils that are heated or chilled by secondary water piped from a boiler or chilled water plant, and then local thermostats in the room. All right. The package system. The package systems are self-contained, and they're weatherproof units incorporating a fan, filters, compressor, condenser, and evaporator coils for cooling. These are DX units. Some of them are small, some of them are huge. I've got a friend that has a commercial HVAC company, and he spends all his time doing commercial work. Some of these units are so big and stuck in the middle of a giant building complex, you got to use a helicopter to set these things, or big cranes. Okay, so this is a rooftop. This would be an RTU, rooftop unit, RTU, and this is everything. It's got the air handler, the whole package. Okay, package systems may be mounted as a single piece of equipment on the roof or on a concrete pad alongside an exterior wall of a building, just like this is over here. This is a complete unit. A lot of the mobile homes use package units, and they tap into the duct system into the mobile home. And the heating and air conditioning, refrigeration units are not inside, they're outside. All right. Rooftop package units may be placed at intervals to serve long buildings, and package systems with vertical shafts that connect to horizontal branch ducts can serve buildings of up to 4 or 5 stories in height. And getting enough room to get a crane in here and a heavy enough crane to get over to set multiples of these is problematic. Now remember in the roof video we talked about that pre-engineered walking paths? Katy Mills Mall will not allow you to get off that walking pad. They will not allow you to take the old DX unit and set it on the roof, even if you put cribbing up there. So you have to take the old DX unit completely off and set it on the ground, swing the crane around to pick up the new DX unit, and swing it up and boom it over to set the new one. And as you get off that walking pad, they'll fine the contractor large sums of money because they don't want that membrane roof tore up. Split package units consist of an outdoor unit incorporating the compressor and condenser and an indoor unit that contains the cooling and heating coils. Now, you may have seen some of these advertised by LG. Life is Good, LG. LG has a neat little system. You can do it yourself if you're a DIY person. You can get these through Lowe's, Home Depot. Just go out and look at LG, get on Google, and you'll see a lot of people that will do that for their shops, garages, or their second-story houses that the normal HVAC system isn't keeping up to the loads. Normally what you'll see is that little compressor, outdoor unit, the compressor and condenser will be on the outside on a pad or even be mounted on a wall of the building. And then what you don't see is the refrigerant lines that go inside, and then there'll be an air handler. That's what I call the air handler. It'll have the heating strips, the fan, and the evaporation coil up in here, okay? Um, and then the air will flow into the room. Um, LG has a whole series of these. Let's see, small thermal units may be mounted directly below a window or in an opening cut into the exterior wall of the served space. The window mounted units are typically used for retrofitting an existing building. Some hotels use these small thermal units, which it's a unit that goes through the wall itself, and sometimes they work, sometimes they don't. Um, um, a window unit, air conditioning unit, whether it's just air conditioning or a heat pump, is a small thermal unit, and they're designed to fit in a window or an opening in the wall. My shop, I put since I had that heater that hangs from the rafters. We looked at the heaters before, thermal heater. In my shop, I just put reframed the wall and put a window unit in there for cooling only, because I had the heater over here suspended from the ceiling joist. So a window unit is also considered a small thermal unit. Let's go on more HVAC systems. What is he telling us here? I think we probably beat this up enough. No, this is something good for you to know. For where y'all are at in your career right now. All right. Factors to consider in the selection, design, and installation of a heating, ventilating, and air conditioning system. Now, most of this is self-evident. Performance and efficiency, both the initial and life cost of the system. We call this life cycle cost. How much fuel and power and air is it going to move per given amount of energy input? Flexibility. Can it serve? How many zones do you need it to serve? So flexibility of the system. The type and layout of the distribution system. Do you have room for heavy ductwork? Or are you going to have to zone this stuff? Space requirements for the mechanical equipment. This is a good rule of thumb. The heating and ventilating and air conditioning equipment of a building can often occupy 10 to 15% of the area of the building. Some more, depending on what you're doing. If you're using a giant chill water system for just a high-rise building, you may require more than 15% of the area. You may have to use a lot of the roof for cooling towers. You drive along 610 over near the Galleria area, you'll see some buildings with cooling towers up on the roof, of the building. In fact, my buddy did some of those. Access required for service and maintenance. Construction requirements for the enclosure. If you're going to put a cooling tower up on the roof, that thing is basically full of water, 62.4 pounds a cubic foot, plus the weight of the structure. Plus the weight of the cooling tower. That all affects your structural integrity of your building. Fire resistance and vibration. Structural requirements, I just said that. Degree of visibility. You may have to put screen walls up because people don't want to see the ugly cooling towers, etc., etc. If you've got internal ducting going up through a high-rise, what about your service cores? Can you get your service people in there? All right. You may have to have a special elevator just for servicing. And talks about the different. Here's a single core, central locations, detached cores, two cores, multiple cores, in apartment buildings and other structures housing repetitive units. The cores may be situated between the units. I'm sure you've seen some apartment complexes where they've had all these ganged out here and feeding individual apartments. Okay. Air distribution outlets. This might be a good place to stop. No, we'll go on. Let me check the 5th edition, make sure we're not losing something. No. Yeah, let's finish air distribution outlets and then we'll go on to water supply. All right. Boy, you could spend your life researching diffusers. What a diffuser does is it breaks up the airflow coming in and scatters that air throughout the structure. The number, the volume, the layout, the pattern, all are determined on how much area you're trying to cover. We saw diffusers like this when we talked about suspended ceilings, did we not? Where the suspended ceiling was actually a air supply, intake and return and supply grid hidden into the suspended ceiling, where the ceiling tiles would hook into here, and this would be your support grid periodically throughout your suspended ceiling. You got the idea that there's a lot of real estate to cover. You go to work for a large architectural firm, or you go to work as a designer in a mechanical firm, you may be spending a lot of time just on selecting diffusers. This is where the program Revit, Autodesk Revit comes into effect. You can build your menu and cookie cutter this stuff through your drawings. So you're not having to redraw each one of these. So these are supply outlets, should be located to distribute warm or cool air to the occupied areas of the space comfortably without noticeable drafts. Remember us talking about the drafts, the speed of the air, okay? These are grilled diffusers. This one has adjustable vanes. These can control it with adjustable vanes, and this will be a floor register. So sometimes they're called registers, sometimes they're called diffusers. Generally, if they're in the ceiling, they're a diffuser. If they're in the wall or the floor, they're called a register. Potato. Don't get all upset. You get it confused, or you get corrected. All right. There's something else you need to understand, and what is the throw is the distance a projected airstream travels from an outlet to a point where its velocity is reduced to a specified value. This goes back to ASHRAE, and the HVAC engineer will determine how far, what kind of throw you need, okay? Theoretically, it should extend at least 3/4 of the depth of the space, and that depends on this surface area. That depends on the surface area of this register. See, I use the right term because it's in the wall. It's a register, not a diffuser. All right, whatever. Okay, but this is depending on the velocity of that air coming out of the ductwork. And if you notice the ISO of that ductwork up there, as it got further away from the air handler, the ducts got smaller. That's because the velocity had to be increased. You got the same air pressure, and that goes back to your air balance. You can't run the same size duct all the way through, or you won't have any air velocity at all at the end, because you'll be sucking it out all the way down the run, right? So if your main source is here, this duct may have to be larger because you're carrying a larger volume, and then you have to make a transition, make it smaller. Then you may have to make another transition, make it smaller, all the way down to get to the end of the supply, where you're going to supply air here and here and here, okay? And these are calculations the mechanical engineer will have to do. based on the velocity, the volume, and the air balance for the room. Okay. All right. Spread S is the extent to which a projected airstream diffuses at the end of the throw. Okay. Because as the velocity of this air slows down, it starts to eddy. Okay. It's basically all they're telling you. It's starting to slow down. It gets a little confused. It doesn't have a lot of velocity to move the air to move it in a straight line. So it'll start to fall off. Okay. All right. And a straight throw is the spread is the total throw divided by a third, divided by 3. A fan-shaped throw, the spread equals the throw. In other words, the distance that it's thrown out, that equals that distance. Again, these are balances that have to be taken care of by your mechanical engineer. All right, this is going to be 11.3, and we'll stop video 2 here. Got to get water into your structure. All right, we'll see you on the next video. Isn't this fun?